Hello and welcome to a new video on IGCSE Classified Physics Paper 4. In this video, we shall be discussing fuses and hazards. Figure 6.1 shows a shower that takes in cold water. The water passes through an electric heater and emerges from the shower head at a higher temperature. The power of the heater is 9,000 watts. The shower is powered by a 230 volt electric supply. Calculate the current in the heater when it is switched on. So the current in the heater is obtained using the equation of power. We know that power is equal to current times voltage. We can rewrite this equation as I equals P over V. And the power here is given as 9,000 watts. So instead of P, we write 9,000. And instead of V, we write 230. And we simply divide them by each other to get 39.1 amperes, correct to three significant figures. In double I, we are told suggest a suitable rating for the fuse in the heater circuit. So the normal operating current is 39.1. This is the normal, and we want the fuse to blow if the current exceeds the normal. However, you might want to ask yourself, by how much should the current exceed the normal for the fuse to function correctly so that it would blow without causing danger? So in the marking scheme, they leave a lot of room for interpretation. Any value between 40 and 60 is considered correct. So if it's just slightly above the normal, if you decide to write 40, then that would be considered correct. Any value between 40 and 60 would be okay. However, if you write something like 70 or 80, this is too much because the normal is 39. So you should not have a fuse that will only blow if the current reaches 70. This is too high. The current is too high above the normal rate. So it has to be somewhere between 40 and 60. Figure 8.1 shows a 240 volt mains supply connected to an air conditioning unit and a freezer. A fuse X is placed in the circuit as shown. The freezer has an operating power of 700 watts. Calculate the current in the freezer. So again, to get the current, you use the equation P equals IV, and P equals IV can be rewritten as I equals P over V. We are given the power, 700 watts, and we are given the voltage as well, 240 volts. So how do we know that 240 is correct here? Simply because the main supply is 240, and these two units are connected in parallel. So the fuse does not really consume voltage. It does not consume a significant amount of voltage that we actually counted in our calculations. So we just assume that it doesn't exist when we're considering the voltage. So therefore, the voltage across the freezer will also be 240, similar to the mains supply. So therefore, here we can just divide 700 by 240, and we get a current of 2.9 amperes. In B, we are told the maximum operating current of the air conditioning unit is 7.5 amperes. Fuses of current rating 1 ampere, 3 amperes, 5 amperes, 10 amperes, 13 amperes, and 30 amperes are available. Suggest a suitable rating for fuse X and give 2 reasons for your answer. So we know that the current through the freezer, this current here, is equal to 2.9 amperes. And the current in the air conditioning unit is equal 7.5 amperes maximum. And these two currents fuse together before passing as a single current through the fuse. So in normal circumstances, we expect the current through the fuse to be the sum of these two numbers, which is 10.4 amperes. So any value of current or any rating for the fuse that is less than 10.4 would blow up in normal circumstances. So the fuse would blow up in the normal operating circumstances if it has any of the ratings inside the blue circle, 1 or 3 or 5 or 10. It would not tolerate the normal operating conditions. So none of these would work. Furthermore, 30 amperes is too far away from 10.4. So the current will be too large. So if the current is at 29 amperes, the fuse will not blow. However, the current will be much higher than normal, which means that there is an abnormality here. This means that there is a danger of overheating and possibly fire. So you don't want the fuse to be so insensitive to current changes, so far away from the normal operating condition. So the optimal here would be 13 amperes. For two reasons. For the reason that concerns the circle on the left, which is that it must be greater than 10.4, so it cannot be any of these numbers, and it must be much less than 30. It must be slightly greater than 10.4, so 13 amperes is the most convenient and the most sensible choice because 30 is too far above the normal operating condition. In C, we are told a fuse is made out of a short length of wire. Explain why fuses of a higher rating are made of thicker wire. So you've studied before that resistance of a wire depends on resistivity, which we don't really talk about that much, multiplied by length divided by area. So why do we need a thicker wire? So we want a thicker wire so that it would have a smaller resistance, because if it has a smaller resistance, this means that there is less danger of overheating. So this is the idea. Thicker wires have smaller resistances and they can tolerate higher currents without overheating. In this question, we're told the packs are connected in parallel to supply a large current to drive the electric vehicle. Explain why it is necessary to use thick wires to carry this current. So this is exactly the same as what we just said. The idea is that thick wires have a large area, so a small resistance. Remember, R equals rho L over A. So thick wires means the area is great. It's bigger than usual. So the resistance is smaller than usual, so they can withstand higher currents. You can use the reverse argument. You can say that thin wires have a larger resistance, and this would create a danger or a hazard of overheating and fire and melting if there is too much current passing through them. You can also mention energy loss, because the higher the resistance, the higher the rate of energy loss. This is also a good point to mention here. Here we're told that the figure shows an extension lead used to supply power to a 3 kilowatt electric heater on a cool evening. State and explain 3 dangers with this arrangement. So this is a very popular question. They give you a diagram and some labels, and you're supposed to figure out what the hazards are in this scenario. So one issue is, of course, the damp grass. We're going to need to talk about the moisture of the grass and how it increases the conductivity and it can lead to electric shock. Now, the extension lead is designed for use with a 25-watt lamp. So it's used for small current, small power. However, the electric heater is 3 kilowatts. So, of course, this is a much higher power rating than what the extension lead is designed for. So this is an issue. Furthermore, there is a cut in the outer insulation, as you can see here. So the wire is exposed, and there is another danger here of electric shock. So we can write these down. First of all, we talk about the extension lead and how it's designed for 25 watts and not 3 kilowatts. And this high power may lead to overheating and fires. Damp grass increases or extenuates the risk of electric shock due to the moisture, especially that the plug and the socket are within this damp grass. So you use these two pieces of information in conjunction together. The grass is damp and the plug is in the grass. It's not on the pavement, for example. Finally, the cut in the outer insulation may lead to electric shock since there are no fuses for protection. This is a similar question. Again, you are given a scenario, you're given more labels here, and you are asked to discuss the dangers of the electrical arrangement. You're also given that the mower cable has thick wires. So thick wires means that they can withstand high current and the correct fuse. The cable is too short, so the gardener uses an extension cable with thin wires. So here is the hazard, because this would work. Thick wires can tolerate large currents. However, thin wires cannot tolerate large currents. Furthermore, there are other hints given in the drawing, which we can discuss and state the hazards corresponding to them. So first of all, we have thin wires. So thin wires have a larger resistance, and this increases the risk of overheating. There is no fuse for the thin wire. So if the current gets too large, you have the risk of electric shock or overheating again. Again, the moisture of the damp grass increases the risk of electric shock. Finally, we are told that the socket is designed for indoor use. So you cannot really put it in the garden in damp grass. Furthermore, it cannot handle such a large current of the electric mower because it's a socket used to charge mobile phones or something that requires a much smaller current. You cannot use such designs for different current requirements. So if you have a socket that usually deals with mobile phones, you cannot use it for an electric mower because it's not designed to handle such large currents. So it's the same idea as the previous question. You are expected to receive questions in the exam that give you scenarios like this one, and you are expected to try to figure out what the hazards of the arrangement are. So this is an important question to bear in mind. This brings us to the end of our video. I hope this has been beneficial. Thank you for watching.